Hello, I'm Utku. I'm studying mechanical engineering in Ege University, and today I'm going to talk about nanotechnology and carbon. For a better understanding of development of nanotechnology, we should first investigate industrial revolutions that impacted heavily our world. Since the development of two-cylinder steam engine by James Watt in the 1760s, humankind has experienced three industrial revolutions. The first industrial revolution, as represented by the appearance of Watt's steam engine, employed various machines to replace human labor. The second industrial revolution began at the end of the 19th century and was characterized by the discovery of the internal combustion engine and electric generator, which led to increased usage of electrical appliances, automobiles, and petroleum products. The construction of the first computer in the 1940s led to the third industrial revolution, which was followed by the rapid development of the information technology. Although many of these inventions and developments provide innumerable benefits, they also pose new and sometimes unforeseeable risks. For example, the appearance of internal combustion engineering led to widespread availability of electric power for lighting, home appliances, industrial machines, automobiles, and aircrafts. However, it also has contributed to the level of air pollution and accelerated global warming. With the rapid increase in populations, combustion of natural resources, environmental pollution, and information overflow, the turn of this century witnessed the birth of nanotechnology. The demand for miniaturized and multifunctional systems has been a driving force for the development of nanotechnology. The concept of nanotechnology was first introduced by Nobel laureate Richard Feynman in 1959 at the annual meeting of American Physical Society at Caltech. In his classic lecture entitled "There is a Plenty Room at the Bottom," Feynman stated, "The principles of physics, as far as I can see, do not pit against the possibility of maneuvering things atom by atom." Later, Nanotechnology from Tokyo Science University first defined nanotechnology as the creation of useful materials, devices, and systems through the control method at nanometer length scale, and the exploitation of novel properties and phenomena developed at this scale. The first scientific paper on nanotechnology was published in 1981 by Eric Drexler, a former student of Dr. Feynman at Caltech. Drexler's idea of molecular manufacturing was followed by his book entitled Engines of Creation: The Common Era of Nanotechnology, published in 1986. In this classic nanotechnology book, Drexler proposed the atom-shaking mechanism to produce machines smaller than a heaven cell and also presented some potential applications of nanotechnology. Although Drexler's publications have motivated researchers in the field of nanotechnology, the main breakthrough in nanotechnology occurred in 1981 when Binning and Roher at IBM Zurich invented the scanning tunneling microscope (STM), the first instrument to generate real space images of surfaces with atomic resolution. This discovery opened up the new important field of nanotechnology and was recognized by the 1986 Nobel Prize in Physics, along with the inventor of the electron microscope. All matter is made up of atoms, with its properties depending strongly on how those atoms are arranged in space. If we could rearrange the atoms in coal, we could make diamond. If we could rearrange the atoms in sand, we could make computer chips. Consequently, nanotechnology as defined to build materials and devices atom by atom holds vast promise for innovation in virtually every industry and public sector, including healthcare, electronics, transportation, environment, and national security. Nanotechnology and carbon. So we got to our main subject. Carbon is the third most abundant element in the universe after hydrogen and oxygen, respectively. Carbon arguably is the most fascinating element in the periodic table, having the ability to bind itself to nearly all the elements. Carbon is the base material for DNA and thus provides the basis for life on Earth. Carbon can exist in several different forms. The most common form of carbon is graphite, which consists of stacked sheets of carbon with hexagonal structure. Under the extreme high pressure, carbon forms diamond, which is a miscible form of carbon. Carbon is important for many technological applications, ranging from drugs to synthetic materials. This role is a consequence of carbon's ability to bind itself and to nearly all elements in almost limitless variety. The resulting structural diversity of organic compounds, the molecules, is accompanied by the broad range of chemical and physical properties. The tools of modern synthetic chemistry allow the tailored essentials in design of these properties by the controlled combination of structural and functional building blocks in new target systems. Nobel Prize-winning discovery of the Buckminster fullerene created an entirely new branch of carbon chemistry. The subsequent discovery of the carbon nanotubes opened up a new era in materials science and nanotechnology. These elongated nanotubes consist of the carbon hexagons arranged in the concentric manner with both ends normally kept by the fullerene structures, containing pentagons. Non-diamonds are the most recent additions to members of carbon family, having the concentric all-carbon structure with usual molecular symmetries. Fullerenes and carbon nanotubes show interesting electronic, photonic, magnetic, and mechanical properties, attractive for various applications. So from now on, we will investigate carbon-based nanostructures. We will first start with fullerene. As is the case with numerous important scientific discoveries, fullerenes were accidentally discovered. In 1985, Crotta and Smalley found strange results in mass spectra of evaporated carbon samples. Herewith fullerenes were discovered, and their stability in gas phase was proven. The search for other fullerenes has started. Shortly after the discovery of fullerene, Crashman et al. Reported the sample weight to produce macroscopic amounts of fullerenes in 1990. The large scale of production of fullerene enables science to study physicochemical properties of carbon clusters with all of the conventional stereoscopic methods and to use fullerenes as useful reagents in synthetic chemistry. Subsequently, other spherical fullerenes were synthesized with a different number of hexagonal faces. Fullerenes in general form are interesting class of compounds that surely will be used in future technologies and applications. Fullerenes packed in Fc structure can be interlaced with alkali and alkaline earth metal atoms, which provide electrons to a conduction band. K-Dub fullerene revealed superconductivity behavior at 18 Kelvin. Physical and chemical properties may be turned via the addition of element and the molecular species into the fullerene lattice within the cage or coating surface of fullerene with transition metals, thereby forming a variety of new fullerenes. Fullerene and its derivatives are considered potential candidates for a number of applications, which includes the following. The hydrogenation of fullerene produces hydrobies. The reaction is resolvable and catalyzed with metals at low pressure. Fullerene catalyzes the conversion of the methane into hydrocarbons and provides Kachen reaction. Fullerene-based capacitors can be used as sensors to detect H2S in N2 and water in isopanel at P' levels. Fullerene can be transformed to diamond at high pressure at room temperature and can also be used at diamond nucleation center during CVD. Fullerenes are used to strengthening, hardening, and improving electrical conductivity of alloys. Fullerene derivatives find several applications in biomedical field, such as inhibition of human HIV, repellation, biological antioxidant, binding special antibiotics to structure of the resistant bacteria, and even target certain types of cancer cells, such as melanoma and light-activated antimicrobial agents. Carbon nanotubes. Carbon nanotubes can be described as rolled-up tubular shell of graphite sheet, one atom-thick layer, which is made of benzene-type hexagonal rings of carbon atoms. The tubular shell is thus mainly made of the hexagonal rings of carbon atoms, whereas the ends are kept by half of them shape of fullerene molecules. Due to their special 1D form, they have interesting physical properties, such as they have metallic or semiconducting electrical conductivity, depending on the celerity of the carbon atoms in the tube. Nanotubes have a large geometric aspect ratio, and they are first nanotubes. Because the graphene sheet can be rolled up with varying degrees of twist along its length, carbon nanotubes have a variety of shear structures. Depending on their diameter and the helicity of the arrangement of graphite rings, carbon nanotubes can exhibit semiconducting or metallic behavior. These similar carbon nanotubes may even be joined together to form molecular wires with interesting electronic, magnetic, nonlinear optical, mechanical properties. These properties allow carbon nanotubes to be used as new materials for development of novel single molecular transistors, scanning probe microscope tips, molecular computing elements, electrical field emitting flat panel displays, gas, electrochemical storage, molecular filtration membranes, artificial muscles, and sensors. Classification of carbon nanotubes. Carbon nanotubes are classified as single-walled carbon nanotubes and multi-walled carbon nanotubes, as shown in the figure. The single-walled carbon nanotubes may bundle into a row of single-walled carbon nanotubes. Multi-walled carbon nanotubes are the nanotubes with more than one graphene cylinder nested one into another. Typical multi-walled carbon nanotubes have an inner diameter 1 to 3 nanometer and an outer diameter of approximately 10 nanometer with the interlayer separation of 0.34 nanometer. Most single-walled carbon nanotubes have a diameter close to 1 nanometer, with a tube length that can be many of millions times longer. Carbon nanotubes can also be classified based on the structure as follows: armchair, zigzag, the shear nanotubes, depending on how the 2D graphene sheet is rolled up. Synthesis of carbon nanotubes. Several methods are used to synthesize carbon nanotubes, such as the arc discharge, CVD, laser ablation. Commercial supplies are currently available worldwide from small laboratory scale to mass production scale. However, to use carbon nanotubes, pretreatment such as purification and surface modification of the carbon nanotubes is necessary. Applications of carbon nanotubes. Carbon nanotubes are the most intensively researched nanomaterials and have a great potential for numerous applications. Carbon nanotubes are used in plastics industry for composite materials, the electrics industry for display or conductive transport films, the semiconductor industry for transistor channels, the energy industry for batteries or solar cells, and the biohealth industry for sensors. Small additions of nanomaterials, such as carbon nanotubes, can greatly improve structures properties of composite materials. Due to their electrical conductivity, carbon nanotubes also have an application for manufacture of low-cost solar cells, electronics, and aesthetic composite materials. Graphene. Graphene is a flat monolayer of carbon atoms arranged in a two-dimensional hexagonal lattice. Rolled graphene sheets represent carbon nanotubes. Because of their unique molecular structure, both graphene and carbon nanotubes possess extraordinary electrical, thermal, and physical properties. These materials are widely used in industry and biomedical fields. Applications of graphene. Graphene was presented as the best possible material for transistor production and could replace traditional semiconducting devices. Since then, a variety of applications for graphene have been proposed. In advanced electronics, graphene has been used for manufacturing of nano and microscale transistors and flexible film displays. Graphene contributed to accelerating interest in smart fabrics, woven textiles for industrial applications, interactive wearable electronics for personal use. In addition, graphene has been used in chemical sensing, biomedicine, and basic science. The molecular structure of graphene can be chemically modified, enabling the attachment of the different molecules of interest. This feature promoted the development of high-performance biosensors. Graphene sensors were designed for the detection of chemicals. Carbon nanofibers. Nanofiber consists of the graphite sheet completely arranged in various orientations. One of the most outstanding features of these structures is presence of plenty of sites, which in turn makes sites available for chemical or physical interaction, especially adsorption. Carbon nanofiber can be obtained in sizes ranging from 5 to several hundred microns on length and between 100 and 300 nanometer in diameter. From electron microscopy studies, it is possible to define sequence of events leading to formation of carbon nanofibers. Carbon black. Carbon black is pure elemental carbon in the form of colloidal particles. It is produced by the incomplete combustion or thermal decomposition of gases or liquid hydrocarbon under controlled conditions. The furnace black and thermal black processes are used to make carbon black, but furnace black process is most common commercial process. The average particle size of carbon black is a few nanometers. Nanodiamond. Single crystals of cubic diamond nanoparticles of an average size 4-5 nanometers were first discovered in 1963 by a group of Soviet scientists, who performed detonation of oxygen-deficient TNT in inert media without involving any additional carbon source. This historic discovery was kept secret for military security reasons until the first open report appeared in 1988. Since then, research in novel diamond nanoparticles has attracted considerable interest, and some industrial production processes have been devised. Although the 1963 discovery has opened up the new way to prepare nanodiamond particles, aggregation remained a serious problem to produce the possibility of their application. Apart from their unusual mechanical properties and environmental stability, nanodiamonds possess a high dielectric constant, high electrical breakdown strength, high operating temperature, and a low dissipation factor of 0.05%. These intrinsic properties make nanodiamonds a promising candidate material for a variety of important applications, such as microelectromechanical systems, field emission displays, electrochemical analysis, and energy storage. Importance of carbon in nanotechnology. It is perhaps surprising to recognize carbon provides a foundation for addressing some of the most serious challenges facing our world. Some of them are demands for alternatives to fossil fuels, drive for efficiency, access to clean water and air, needs of aging population. For example, lithium-ion batteries used in electrical vehicles won't work without carbon. Modern-day water filtration systems need carbon to capture impurities. Materials processing depends on carbon for lubrication, and synthetic diamonds used to protect materials in erosive industrial environments are made from carbon. The new class of carbon materials and chemicals that nanocarbon manufacturers will have a greater and more profound effect than existing forms of carbon in shaping solutions to the four challenges listed before. Nanocarbon's innovations are derived from its competency in the chemistry of these new forms of carbon, enabling its customers to shrink the size of new generation semiconductors, make flash memory more energy efficient, provide healthy metal-free electricity for display, create low-cost organic electronic medical devices, develop low-cost solar cells, develop lightweight, lower-cost fuel cells for transportation, make batteries that can be printed, create water filters that won't fall, capture free radicals before they can damage cells, create X-ray sensors that limit radiation exposure. Thank you for listening me all the way. My references are here, and I wish you have a very good day.